Welcome back to another video. Today we're going to take a look at Assignment C, or I guess right now we're going to take a look at Assignment C. I'm going to do my best to get as many of these videos out. I'm going to Assignment C before Assignment B to make sure that all the students have an opportunity to see the solutions to the most recent assignment that they might not have had an opportunity to get through office hours or tutorial sessions. So let's take a look at question 1. Consider two parallel mirrors depicted as W1, W2 at a distance of 5 from each other. A source S and a target T are located between the mirrors at respective heights S1 and S equals 1 and T equals 2 from W2. Assume the horizontal distance between S and T is D equals 10. At what angle, say phi, should a ray leave S so as to reach T after one reflection on mirror 1, on W1? Okay, so essentially a problem like this, it's a little bit of an introduction to waveguides, right? In wireless networks, this becomes a very serious issue even for computer scientists, although in general waveguides is a topic for electrical engineers and physicists. So we are going to need exactly one concept, Snell's law. So let's draw this out and I'll explain Snell's law really quickly. So if I have an ideal interface, right? So an ideal interface meaning a line, right, for a drawing purpose. But this would be a perfect mirror, right? Some sort of surface that when a ray hits it, 100% of the ray returns with a phase shift, right? So let's explain this from the concept of a phase shift. So I have a ray that comes in, and a ray is a vector, right? It has a magnitude and it has a direction. The direction that it has is into this interface at some angle of incidence. So this concept is also called specular reflection. So wherever it's incident, we draw a straight line, like perpendicular to the interface that it is incident upon, and we say that this angle here, which I'll call theta, is equal to the angle of reflection, and of course the ray's magnitude has been flipped, so it's equal and opposite. And this, again, this is for a perfect interface, like the interface of question 1. So this would be any type of perfect interface, just like our W1 is such a perfect interface, right? So then this angle out would be theta as well. Okay, so now let's actually take a look at the problem in the question, right? So knowing Snell's law, or knowing just this little piece of Snell's law, gives us exactly all we need to do, all we need to know to solve this problem. So let's draw out our little waveguide here. I'm going to draw W1 as a solid line and W2 as a dashed line, and I'll explain why I do that in just a second. Well, I guess I'll explain it while I'm drawing it. So W2 is never going to interact with your wave, with your ray. So when we're considering the ray trace of this ray, we never really need to consider W2. It's just here to give us a reference for heights. So here's W1. W1 is the interface that we'll actually be interacting with. Now, let me get this out of the way. Alright, so now S is much closer to W2, so I'll draw it like this. So here's S, and T is about twice as close to W2, so I'll draw it around here. Okay, so we have a ray coming up. Let's see, this is going to be kind of tough to draw well, but hopefully this works. Okay, yeah, not bad. I mean, it's not quite perfect. This should be square, right? Well, not necessarily square actually. So no, this is good enough. Okay, good enough. So now I have a specular reflection here. So draw my arrowhead to indicate that this is a vector quantity. Okay, and now I draw my line which is perpendicular to the interface of reflection. Okay. And I'll extend this a little bit farther than I need it to be. Oh, that was supposed to be a little bit longer. Alright, so now where do we go? Well, we know that this angle, which I'll call theta, or theta, yeah. So this angle here, I know that these two angles are the same. I know that the ray's magnitude is opposing. So whatever this came in, this comes out the opposite direction. Now to solve this problem, you just need to know, I guess, which little bits of geometry you would want to solve this with. So I think the best bet here is to just draw another horizontal line parallel to W2. If only I could get this felt tip pen to actually contact the paper. So okay, so I have a 90-degree angle here, and now I draw one more horizontal line up here. This pen really doesn't want to come into nice contact. Okay, so and then this is another 90-degree angle. So what we've done here, because if this is the angle, do we have the name for the angle? We say phi. Okay, so I have this angle phi. So knowing that Snell's law exists, like knowing what we can do with the Snell's law, helps us understand that these two triangles are in fact similar triangles. So if this is theta and this is theta and that is phi, then this must also be phi because this is 90 degrees. So now we absolutely have similar triangles. Okay, so I'm going to draw a little line down here, and I'll draw another little line down here. Just extend that a little bit. And then this distance here is a distance of d. Okay. So I'll call this distance here, this is a phi, so I'll call it p. And this is also a phi, so we'll call it, how about I do this? Instead of calling it p, I'll call it a, and I'll call this b. Alright, so at this point we basically have the grounds for a solution. So let me make sure everything's in the frame. Yeah, looks okay. So what we need to know for sure is that the height from S to here is 1, the height from here to there is 2, and then of course we need to recall that this height is 5, and then d equals 10. And now we have our answer in one form or another. So the next thing that we do is we recognize that the tan of alpha, right, or the tan of phi, is this distance here divided by this distance here. So tan phi is equal to this distance, which I haven't named yet, but I'll call this x. Okay. Now, I know the distance that x is, right, because I know that W1 to W2 is 5, and I know that the height of S is 1, so then x must be 5 minus 1. Okay, so I have 5 minus 1 divided by this length a. Now I have no idea what a is, right? Not yet. And I can also say another equation for tan phi, right? Tan phi from this similar triangle is this height, which I will call x sub 1. This x1 divided by this b. Now, I know the length of x1 because this is 5 and this is 2, so this is 5 minus 2 over b. So let's clean that up a little bit. That's tan phi is equal to 4 over a, which is equal to 3 over b. Okay, so now I have an equation that relates a and b through the tan, and I also have an equation that relates a and b through d, because a plus b is equal to d. So a plus b is equal to d. which means that a plus b is equal to 10. So I guess these are our two important statements. So I'll put a little 1 here and a 2 there, because with 1 and 2 we solve this problem. So remember, we want tan of phi, but first we have to find a value of either a or b. So what I'll do here is I'll take this fraction here and find an equation for a. So the easy way to start is just to take this whole thing, 1 over it, so a over 4 is equal to b over 3. So then a is equal to 4/3 b. Let me make sure this is in the frame. Yeah, okay, it's nice. Not too bad. Alright, so if a is equal to 4/3 b, then I take this 1, so I say 1 into 2. So then 4/3 b, right, I took this value of a and I plugged it in here. I guess plugged is not the right word. I should say I substituted that equivalent value of a for a in this equation. So 4/3 b plus b is equal to 10. So, alright, I need a similar fraction. So I multiply this second b by 3 over 3, right? Just to get the bases the same. So that's 7/3. So 7/3 b is equal to 10. And thus b is equal to 30 over 7. Okay, so now I'll call this 3. And I guess this is our first equation, so since I already numbered this part of it as 1, I'll call this part 0. So now I need some space on my paper. I guess I'll pick this top corner. Is this top corner well in? Let's pick that bottom corner. Okay, so now I say 3 into 0. 3 into 0. And I'm going to look at this part. So 0 specifically corresponds to this part. Because I have a value for b, I don't know a, so I'm solving from this side. Of course, you could have done the equivalent, and instead of solving for a, you come up with a solution in terms of a here and b here, and then you substitute b in. It's the same answer, but a different path. So, okay. So, let's see, this was a 5, 4, 3, right? So, yeah. So now tan phi is equal to 3 over b, and b is equal to 30 over 7. So I'm actually going to scratch that and say tan phi is equal to 3 over 30 over 7. So the 3 and the 30, we can divide that into a 10. So we have 1 divided by 10 divided by 7 gives me 7 divided by 10. And now that's the tan of phi. So finally, the tan of phi being 7 over 10, I basically just take the arctan, right? So the arctan of 7 over 10 gives me phi. And that's your answer, right? This is almost, it's a little bit more than 34 degrees and a little bit less than 35 degrees. You don't have to put that in terms of degrees. The arctan of 7 over 10 is good enough. And the reason why the arctan of 7 over 10 is good enough is because that is a exact solution. Everything else, if I put a number in, is an approximate solution. So there's really no point to go to an approximate. Consequently, saying that the tan of phi is 7/10 is equivalent to giving me an answer for the angle, right? It's basically the same thing. So that's problem number 1 solved in a nutshell. What you had to do here was take advantage of similar triangles, which is, I guess, grade 11 math. If you knew Snell's law, which is grade 11 physics, then you have this similar triangle done very easily, right? So we got this portion here with Snell's law, If you didn't know Snell's law, there's another opportunity here. You just simply extend the length of this ray and extend the length of this ray. And so what you can do now is take a look at what similar or what angle theorems you can use, right? So now I can oppose this angle. So again, I don't remember the name of this theorem, but if we extend out here, we get the opportunity to use opposite angle theorem and then that theorem with the two parallel lines. So of course this angle would also be phi, right? And then this angle here, let's see, here would be theta, and then this angle here would be phi, and this is a straight line, so then I know that phi and theta equal 90, so I can come back here and recognize that, hey, this must be phi, right? Okay, so that's how you would solve it without Snell's law, but if you knew Snell's law, you don't have to worry about that. So this is the, I guess, the short and long answer for question number 1. I'll see you in the next video for question number 2.